think so. So I start the recording, I think. Yes. And so we are very happy to welcome Balaji. Most of you know him, I guess. So Balaji is working at the GFDL laboratory at NOAA. And Balaji was in France for Make Our Planet Great Again fellowship in between 2017 and something like 2022, I guess. Balaji, you may complete that if you like. And Balaji is heavily implied. Sorry, I have a waiting room at the same time. Balaji is heavily implied, in particular at WGCM. So on the international level, in thinking about the infrastructure of climate modeling and organizing and developing all the scientific requirements for the infrastructure linked to the CMIP projects. So Balaji is deeply thinking about what are the CMIP projects and what are GCM used for and made for. So today, Balaji is going to present his recent work on are GCMs obsolete? So Balaji, the floor is yours. We will take questions at the end. So please, you can write questions already in the chat, or at the end we will give you the floor through a process of raising your hands. Thanks in advance. And don't forget to switch off your mics. Thanks a lot.
Okay. Thank you, Juliette. I hope everybody can hear me clearly. One update, in the last 3-4 weeks, I'm no longer with GFDL anymore. I've joined a foundation called Schmidt Futures, as it's shown here. We can also talk about that if you're interested. But my talk here is on this title, are General Circulation Models, or GCMs, obsolete? And you may wonder why anybody would ask such a question. Who exactly is saying that they're obsolete? In fact, there's 2 directions in which this question is being posed. One is coming from people who believe that the process of creating a general circulation model, which is to resolve the dynamics to whatever degree you can based on the available computing, and then whatever you are unable to resolve with your model, you try to parameterize. The one set of arguments is saying that that process is not working anymore, and we should just forget about parameterizing certain things like clouds and just go directly to very, very high resolution models where all these things are actually resolved. So that is one set of people saying that the traditional GCM should not be used anymore. From the opposite direction, from the IPCC perspective, people are, what was actually a surprise to me when I found out about it last year, is that for many results, they're finding that the GCM results are not good enough, and therefore they're using emulators to get some of their results. So in this regard, one of the people in the audience, Ben Sanderson, gave a talk at the WGCM meeting last December in 2021, which was for me extremely an important talk, in which he said that GCMs have actually become a secondary line of evidence for IPCC. So in 2 directions, people are saying that maybe the traditional GCM is not that useful anymore. So I want to, in this talk, how do I go down? Okay. I will talk about what the GCM is, starting from the work of Shikuro Manabe, who got the Nobel Prize in Physics last year in 2021. What are the constraints on the GCM going in the same direction as it has been going for the last 30-40 years? And I think that comes from computing technology. Some of you have heard me talk about this before. Computers for a long time have been getting bigger, but not getting faster. And then, so we'll talk about emulators, which are used in 2 different ways now in modeling, one of which I feel is like a way to actually improve the GCMs using emulators for calibration. Some of it is based on work done by people in the audience. I saw Fleur here. I hope others who have been working in this field are here as well. And then I'll talk about the idea of GCMs obsolete. And I think I've already given you the indication that I'm going to argue that the GCM is still extremely necessary for our science. So let's start with where we began the work of GCM. So one of the first papers is Manabe and Weatherall from 1967, which is a 1D model response to CO2 doubling. And in this model, there's two processes going on, and they're both in the vertical. One is that the Earth is warm, both from radiation, the Earth is warmed at the surface and it's cooled aloft. So that causes the temperature gradient, the vertical temperature gradient to increase. And if it increases beyond some critical value, you will get convection. That's the traditional Rayleigh-Bénard convection. And that will serve to restabilize. It'll decrease the stratification of temperature in the atmosphere. And these two will eventually come into equilibrium, which they call which Manabe called radiative convective equilibrium. We call it RCE. It's the asymptotic state. So you start from any initial value and you keep running the model for a long time. And this vertical redistribution of heat will eventually cause this particular kind of profile to appear. I hope you can see my mouse moving. And it's basically as a function of relative humidity, as a distribution of relative humidity, you can deduce what the lapse rate will look like. And what they found was a very interesting result is they increased the CO2, which is radiatively active as a gas, and also has some feedback effects with the relative humidity. If you put these two things and you keep increasing the values of CO2 going from blue to black to red, you find that the surface temperature increases by many degrees. So this is the first result showing that if you keep doubling CO2 and quadrupling CO2, you're going to get a surface temperature response. They went on to build the first 3D model. This is the first couple model. This is Manabe and Bryan, which was recognized as a milestone. You can see that it's a highly simplified land and sea atmosphere with no poles. It's the best that they could do with the computing technology of that time. And eventually they also did the energy, I mean, the heating is not just simply distributed vertically, it can also be redistributed horizontally. So you have to take both of these into account. And so they built this now with the first 3D model, atmospheric response to double CO2. The dots are the observations of the time. This is temperature as a function of latitude. And again, you see that doubling CO2 causes the warming almost everywhere. So when you increase both vertical and horizontal redistribution of temperature, you still get, and you go to the equilibrium response to double CO2, you still get warming everywhere. And the equilibrium response is important. So they showed here that even though the system is chaotic, if you can start, but even so, for short term, the chaos is an important factor, but the equilibrium response is still the same. So they start from a very warm temperature or a very cool temperature, and you let it run long enough, and you will eventually get equilibrium temperature. In this case, you see that they ran for around 700 days or about 2 years to get equilibrium because they have a highly simplified ocean. Nowadays, when you take the 3D ocean state into account, the deep ocean circulation takes a very long time to equilibrate. So normally today, the equilibration or spin-up time of a modern GCM can be measured in thousands of years instead of 2. So what does a GCM look like? It looks somewhat the same from those days to this day. So essentially, you discretize the equations of motion on the sphere. Here you're showing a simple lat-long grid, but today we use more sophisticated grids, completely unstructured cube sphere, and so on. In each grid box, there is a column, and there's a lot of physics that goes on inside the column. Everything that is unresolved is shown here. Clouds, some circulation in the ocean, land surface. So ecosystems also go inside these columns. And these columns can also exchange data amongst each other. So there's horizontal exchange between columns. So this is what a GCM looks like. So if you see from there's been about a 10x increase in the resolution over about 50 years between the Manabe and Bryan paper, which is 1969, to CMIP6, which is 2019. So from about 500 kilometers, we got to about 50, maybe many models are still running less than 50 kilometers in resolution. So parameterizing convection is one of the more hardest problems in this because clouds can both trap heat and they can also reflect heat. So in order to model the effect of clouds, you need very precise and very sophisticated models. And you can see many kinds of clouds can exist within a grid column. So typically what people have done for parameterization, this is one of the classic papers of Arakawa and Schubert. They said that there's a population of clouds inside a grid box, and it is in quasi-equilibrium with the large-scale environment. So the large-scale environment is trying to destabilize, and the clouds are trying to restabilize. So these two will come into quasi-equilibrium. And you can parameterize by making certain closure assumptions about how the quasi-equilibrium works. And so this is all happening within the grid column. Some people have argued that the progress since the time of Arakawa and Schubert, or even since Manabe, it has been extremely slow. David Randall, who has worked a lot with cloud resolving models, called it a problem that refuses to die. And so this column abstraction for describing clouds has been decided that many people feel that it can never be solved. There's too many cloud habits. Convection is not happening column by column independently because there is organization on large scale in the form of squall lines or tropical cyclones, mesoscale systems. So from a column perspective, this is non-local. So, and then there's a lot of the small scale dynamics. You can have updrafts which are taking place on very, very small time scales, and the entrainment is a turbulent mixing process. Downdrafts can create cold pools or density currents at the surface, which can again create convergence and start new convection. All this is happening as extremely small scales. Inside the clouds, there is microphysics, which is basically cloud droplets aggregating, coalescing, freezing, and many kinds of processes which are happening obviously at micron scales or even lower. So what happens is that when you start to develop parameterization, you start with a simple idea, and slowly as you try to match the data, it becomes more and more complicated. So this is the problem of Ptolemy when they try to start with a heliocentric system to try and match the positions of the planets. So you initially start by saying there are orbits, and then you find in order to match it, you need to have cycles and epicycles and so forth. So it becomes more and more complicated. And despite doing all this work, there have been some systematic biases which have not gone away for many decades. So this column abstraction, according to some people, is just broken, and we should just not do it at all. So what can you do? You can go to extremely high scales. So this has been done for a very long time. So this is not a new problem. So convection resolving models have existed since the late 70s. So this is one of the earlier versions. This is one of the older cloud resolving models. This is obviously not a global one. This is just inside in a very simplified radiative convective problem in a doubly periodic Cartesian domain. And you can see, however, that the cloud population, it does look as complicated as this picture that is shown on the left here. So you can get the realistic ones. In the boundary layer, if you can, so that is around kilometer scale. In the boundary layer, which can be maybe on the marine boundary layer, can be on the order of hundreds of meters deep or maybe a few kilometers deep over the continent. You have boundary layer clouds. Let's say you have an inversion of the top of the boundary layer. You have very, very small scale clouds, which can be in the form of trade wind cumulus, which are very tiny clouds, or it can be in the form of stratus, which is the entire field is covered by clouds. In order to model these with turbulence, you do what are called large eddy simulation models, and these typically have to have a resolution of around 10 meters to do this problem correctly. So these two approaches obviously cannot be done on a global scale. So people started talking about embedding these cloud resolving models inside GCMs. So from Randall, so for example, what you would do is that you have a grid box, which is still quite large, hundreds of kilometers in size, and you put a cloud model inside that. And in this case, they can only afford to do a two-dimensional cloud model, so that's what they do. So, and then you can maybe, if you want to have dynamics in both directions, then you can put two CRMs, which are both two-dimensional, but they're orthogonal to each other. The importance is that now you can get some non-locality in time also. The CRM can retain the memory of its own state, so there's continuity from one time step to another. And you can connect CRMs to the neighboring column CRM, so you can get mesoscale organization. It's still very expensive because if you think about it, in every single column of a GCM, you're running a separate model, which is the cloud resolving model. So there has been some improvement in the climate simulations. For example, a phenomenon called the Madden-Julian oscillation in these models is typically better. And then they also try to do it for boundary layer clouds. They call it now ultra parameterization if you put an LES inside a cloud model. And because now there are these super parameterizations has been used for, now that you have this cloud resolving model in each column, and you have a lot of data from that, you can actually train machine learning using that. So there's been some papers looking at that as well. So the issue of this, what resolution? So I said for boundary layer, you need around tens of meters, and for deep convection, you need about 1 kilometer. If you just look at it as a turbulence problem on the planetary scale, so this is the length scale in a log scale in kilometers, and this is the spectral energy density. At very large scale, you have essentially two-dimensional spherical geophysical turbulence, which is known to have a -3 slope. And then you get into three-dimensional turbulence, which has a -5/3 slope. And that continues down to almost any scale until it continues down to what's called the Kolmogorov length scale. So if you're anywhere in between from 100 kilometers to 10 kilometers to 1 kilometer, whatever you do, you're going to have to truncate the spectrum somewhere. So you choose some resolution, whatever you can afford on your biggest computer, you truncate it, and you try to represent everything that you've not resolved. You have to parameterize it. That problem is not going to go away. You can go down to a 10-meter scale, and you're still going to be parameterizing something. So there are ideas called backscatter, for example, which is a theoretically consistent way of separating the resolved scale from the unresolved scale. But physically, there is no separation. Any scale you pick, there is a large scale and there is a small scale. That never changes. In the ocean, it's an even more complex problem because of the existence of bathymetry, which is that the ocean has a depth which varies from area to area. So in this study, what you're looking at is there are these eddies, and whether you need to resolve the eddies or parameterize them depends on a length scale which is known as the baroclinic deformation radius, or the Rossby radius. And you compare that with the resolution of your model, which is delta x. And at what delta x, what resolution of your model do you resolve this Rossby radius? And you see that in some areas of the globe, you resolve it at very large scale. So at half degree or 1 degree, 1 degree is equal to around 100 kilometers. So in the equatorial zone, it's quite well resolved. But there are many areas where you can get down to 1/50th of a degree, which is around 2 kilometers, and you're still not resolving the Rossby radius very well. So in the ocean, you will never get to a length scale. It's very unlikely you will ever get to a length scale where you will be resolving all these processes fully. And here, because there is no scale separation, you cannot do, at least as to my knowledge, the idea of super parameterization will not work. So you will be trying to resolve these things or parameterizing them at any length scale in the ocean. So this is a picture from a simulations called Untitled 60, which was done in Grenoble, which is running at 2-kilometer resolution for the North Atlantic. So people have argued that you can get to the point where cloud resolving models are as good as good indeed. So this is called a kind of Turing test. So Turing is the original Turing test by Alan Turing is how do you recognize human intelligence from artificial intelligence? And if you cannot tell the two apart by asking some questions, Alan Turing said that you have passed the artificial intelligence test. Similar argument for climate is that if I show you all these pictures, some of them are coming from models and one of them is coming from a satellite. Can you tell which one is a satellite? Obviously, from an instantaneous picture, you probably cannot tell. But from other tests, you may be able to tell. But the Diamond project is trying to say that we can get to global cloud resolving models, which will not have the problems that GCMs have. How much has model resolution evolved? I showed you that it was not very high. It was between the time of Manabe to today, it's maybe 10x at best. And here, this paper from Tapio Schneider's group is showing that computing power is growing at a certain slope, which is called Moore's law. I'll talk about this in a second. But the resolution of models is actually not even doubling at the same rate as the computing technology. So the horizontal resolution you can see is growing at a smaller scale. The blue dots are the mega flops. So how big a computer is measured in floating point operations per second. That's plotted on the same large scale here. It's a function, this is between 1980 to 2020 or so. If you can get to below a kilometer, so 10 to the -1 or 100 meters, or 10 to the -0, which is 1 meter, you may get there if you continue on this path. I'll show you that we're not even going to continue on this path, but the models are definitely not keeping pace with that anyway. The other thing is that we do not simply want to run one simulation at the highest resolution that will give you good results of some kind of prediction model. We need to go for the climate problem well beyond prediction. And the reason is that there's multiple sources of uncertainty in our models. One is just chaotic uncertainty, which I mentioned before, that it's very sensitive to initial conditions. But in this paper, which is shown from Hawkins and Sutton 2009, that eventually the fraction of uncertainty, which is chaotic, goes down with time. There is a second uncertainty shown in green, which is called scenario uncertainty, which is how the external forcings like CO2 are going to change with time. And that we don't know because it depends on policies and politics, so we don't really know. So we have to always sample a wide range of possible scenarios. And the third thing is what is called structural or epistemic uncertainty, which is the unknown physics or the unresolved physics and the fact that you're failing to represent them well. So in order to do the climate problem, it is not the same as doing a weather prediction problem where you're just trying to run one simulation or an ensemble of a few simulations to just do a prediction out to a few years. You're going to have to sample a lot of things which I call counterfactuals because they do not happen in nature. We're trying to say if there is a CO2 policy or if there is no CO2 policy, what is happening? We are going to sample multiple values of physical parameters because they're fully unknown. So in order to do this, we have to be able to do hundreds of simulations, each of which are hundreds of years long. And I've said that you should also be able to do them in a short period of time, which is measured in months. Because if you start a simulation and you have to wait years for the answer, then you may lose interest in what you may forget what question you were asking, for example. The other problem is that if you're thinking about climate as a prediction or a forecast problem, you're likely to be overfitting to present-day climate. And I'll revisit this in the context of paleo. But this is an interesting study which is showing, for example, so there is the Hadley cell is a measure of tropical circulation. And the blues here are showing from a large range of CMIP5 models that the prediction of climate models is that the Hadley cell circulation strength is actually going to decrease with time over the 21st century. And this is quite consistently shown across many models. Similarly, you can take a single model and run a very large ensemble. So it may be just the chaotic uncertainty you're sampling here. Even there, with a large ensemble of a single model, you're seeing the decline in the Hadley cell circulation. The green is very interesting because these are what are called reanalysis models. These are forecast models which have been run for a long period of time. They're also showing that over the last 20, 30 years, the Hadley cell actually increased, which is the opposite of what the climate models are saying. And why is that? This is a very interesting paper which is arguing that actually the reason is that the forecast models, because they're using data assimilation, the reanalysis models, they're actually correcting the model to fit them better with observations, but in doing so, they're violating certain conservation laws. So they're arguing that there is a distinct possibility that the models are actually correct, the GCMs are actually correct, and it's the reanalysis which is falsely giving a signal of increasing Hadley cell strength. So this is something we should be concerned about. Quickly switching to computing technology. The reason why I believe we won't stay on that doubling curve for a long period of time is because here is what has been happening over the last 50 years with the logarithmic increase in computing. That's called Moore's law. Every 18 months, you double the number of transistors you put on a die. And the number of transistors is still growing. It's still growing or you can argue on a log curve. But the important thing to pay attention to is the frequency, which is shown in green here, which is the speed of one arithmetic operation. How many can you do? It's the clock speed of the chip. That, as you can see, has not increased at all for over 10 years. It plateaued in 2010. It has never changed. And because of this, what this means is that you can solve bigger problems in the same time because you can parallelize over a bigger scale. That's called weak scaling. Strong scaling, which is the same problem, if you get a new computer, it will not go faster because the same problem is going to be parallelized the same way and the arithmetic speed is not changing. So there was a period of time, if you go back into the early 2000s, where even the arithmetic speed was changing. So if you had a problem, you had a model, if you waited 2 years and bought a new computer, you would solve the problem twice as fast. That's no longer the case. So strong scaling does not exist anymore. So even if you get to an exaflop, so this is a paper from 2019, which is saying called exascale be the rescue. It's talking about as you get to exascale, as you increase it, exaflops, what will you resolve? So let's say you get down to 1 kilometer and you will resolve deep convection in the atmosphere. Even doing that, what they predicted in these models is that you still need a huge improvement, about 17x, to get to 1 simulated year per day, which is considered kind of the bare minimum for doing climate problems. And you remember that in order to do CMIP kind of experiments, you need to run thousands of simulated years. So you need to be able to run that. So here they show that even if you use the whole exascale machine, they will be able to, it will take them several days to run one simulated year per day. And the question of running thousands of simulated years does not even exist. However, the counter argument is that all the uncertainty associated with cloud parameterizations will go away. So you can they call digital twins and so forth. And you can argue that that may work. Let's not forget also that the ocean is also important. It's very important on any scale longer than a few months. So deep learning has become an attractive solution for this problem, and there is a reason why. So if you look at the problem of these arithmetic, where the arithmetic is not getting faster, but you can do a lot of arithmetic in parallel. Look at a problem where you're trying to do a regression problem where you have an input vector and an output vector, and you're trying to find the best match between them. Normally, you can say that there's 5 inputs and 4 outputs. So there's about 20 operations if you're doing a linear direct regression. What neural networks can do is that they allow you to place an interior layer of hidden variables called neurons. And now each black line represents an arithmetic operation. Now you can see that instead of going from 5 to 4, which is around 20 operations, you're going from 5 to 8, which is 40, and then 8 to 4, which is 32, and so 40 times 32, which is around 1,200 operations. So the number of operations has gone up dramatically. And if you go to deep learning, you can put multiple layers of neurons. It goes up astronomically. So you can do a lot of algebra for the same inputs and the same outputs. So dense linear algebra works very well on these new machines, which are parallel with the fixed speed of arithmetic. So because of that, deep learning has taken over the whole world. And people are trying deep learning techniques to do various things. One, for example, is saying, do we even need models anymore? Can we just simply I can give you inputs and outputs and you figure out the relationship between those? And this is a study showing you can actually do that pretty effectively. You can, for example, learn a chaotic time series quite exactly, and then you can reproduce it exactly out to many Lyapunov times is a time for a chaotic time series, how fast you can, how long that you retain the memory of the initial conditions. And the longer you can retain it means that you really learned a chaotic time series very well. But this works because the parameters of your original equation are not changed. Climate is non-stationary. And that means that if you learn on the present day, it does not mean that the same learning works for the future because the climate has changed. So one thing you can do instead, you cannot, so I don't think model-free predictions, it may work for weather. I don't think it's going to work for climate. There's a chance that it can work for stationary problems. What you can do for non-stationary problems is use more complex models, which are called up the ladder, meaning like using a cloud resolving model to train a GCM. And so here is another study. Very quickly, I'm going to mention this study. So it is comparing GCMs with cloud resolving models. And you can see that the spread in uncertainty and they're running the same experiment, which is the radiative convective equilibrium experiment. The CRMs, which is the model up the ladder, which is a model that is resolving some of the process we are trying to parameterize, reduces the uncertainty somewhat, but not by a lot, is what this study is showing. Similarly, you can use larger simulations. So here again, what you're showing is that there are at various sites around the world, you're comparing 2 GCMs from the CMIP-6 experiment, CMIP-5 experiment rather. And this is showing the level of error between them. So red is a high level of error and dark blue is a low level of error. And so there is quite a spread between the models. But if you use LES models, which are using the GCM data as input, as their mean conditions, you can see that you can reduce the uncertainty by quite a lot. But on the other hand, the LES models themselves have a lot of details, which some of the people here have worked on, and it's sensitive to some of the details as well. So how do you use emulators to solve the problem? So what we are trying to do is, I've already introduced this idea of the ladder, which is a paper that has been published, which the link is here, called Charney's ladder. Charney, the original in 1950, he spoke about, he built a very simple model for the first computer, and then he said, I can build more complex models in the future, and he called it going up the ladder. So if you can use these models, which are hierarchies of models, and you can go from one to the other. That is, you run a model at very high resolution for an idealized case, and then you learn from that in order to build a GCM or a parameterization using some sort of cost function. So this is the way that we are trying to do it. So we can say that we can calibrate models like GCMs using these very high resolution simulations. So the way you do that is you write a cost function and you say that you have certain set of observations. You have about n different metrics, and you try to minimize the cost function by varying some parameters. So this is what you're trying to do in calibration. I'm going to skip this slide because I'm going to get to the details. But you have a choice of cost function, right? So this is an example from the tuning of the last gen DFTL models used in CMIP6. So they have a choice between doing two things. They're trying to minimize some error in the cloud field. And you can either minimize it in some areas like shown here, where there is large biases in the model, or you can reduce the error over the whole cloud field across all of space. So they showed that they have a choice. There is one tuning at which they reduce the error locally. You're going from this figure to this figure. You reduce the local error. What that causes to happen, it makes the global error go up high. So you have to choose always between whether you want to minimize local errors or global errors, for example. So this is where the choice of the cost function, or what Frederick Houdin called the art of climate model tuning, comes in. You have to make these choices, which element you decide to tune actually. And what they showed, again, I'm not going to go into this. These are just references I leave for you, but they say that we hypothesize that the development of a climate model is optimized in close coordination across component models. That is, they cannot tune each component separately and then couple them. Similarly, they say CM4 is sensitive to a number of features which is much less apparent in uncoupled atmosphere land simulations. So the tuning of it, by the way, took around 50,000 simulated years. We submitted around 10,000 simulated years for CMIP. So you can see, you think of it as 5 times the cost for just tuning the model as we did for the actual scientific runs for CMIP models. And again, you have all these choices. Should you get the 20th century simulation correctly? So this is from the CMIP3, the previous CMIP experiment. GFTL submitted a run which had the green line, which is shown here, the CMIP5 model. In the 20th century, this is the time series of 20th century global mean temperature. It had quite a large cold bias in the last half. And later, after submitting it, the author Chris Golas showed that if he had chosen, he could have chosen to get temperature right in the 20th, in the later half of the 20th century, but then you get the last part of it really diverging a lot. So you have to make all these choices while tuning a model. So, and it's very expensive to do it using GCM. So the goal of this problem of using emulators to parameterize models is to explore the parameter space while minimizing the use of expensive forward models. And the way you do that is, again, this is from the HiTune project from France. You write, this is a different form of the same equation I wrote. Lambda is the parameters. You vary the parameters lambda in order to minimize a function which is called the implausibility function. Here we are not, the important thing is you're not trying to optimize the value of lambda. What you're trying to do is to remove all the values of lambda, the vector lambda, which cannot satisfy the boundary cannot satisfy your data, whatever you're calibrating against. So if you can, you try to get your implausibility below a tolerance, and a certain area of parameter space lambda will be left, which is called the not ruled out yet, or NROI space. And you can do that in multiple waves. Each time you get an NROI, and then inside that NROI, you apply a different metric and you minimize it still further. So it's the intersection of all the NROIs, which is your final answer. If you can minimize that space effectively, then you have a small number of parameters which you explore using the full using the full GCM. So here is the paper from Fleur Couvreux et al. So they're using a large eddy simulation as a reference, and I won't go into the details, but you're using different levels of emulators. Your parameterization is written in the form of a single column model, which you're trying to calibrate against the LES. You're using a thing called Gaussian process for emulation, which works very well within the range of the data that you have. It's basically saying that if these data are correct, there's a Gaussian distribution of possible trajectories. But as you can see, when you go outside the training range, they vary quite a lot. They will diverge. So you have to stay within your training range. And you end up with figures like this, which is, here it's just a test. So the black dot is the truth that they're trying to emulate. And they showed that the NROI space is actually quite effectively finding the space of parameters which includes the true value that they're testing in this perfect model setting. And sometimes what can happen is that the NROI space actually goes to 0. That means it is saying that there is no value of parameters which can possibly fit your training data, which means that your model has an error that you must fix. So that's what that means. So it's just a list of papers on this field. There's another project in Tapio Schneider's group, which is using a similar method, which is called calibrate, emulate, sample. Again, I won't go into the details, but you can, I've given you a lot of references for you to read about this stuff. But it's trying to do the same thing, which is trying to calibrate approximately here. The parameter vector is called theta instead of lambda. You calibrate it using the full model, using a method called ensemble Kalman inversion, which you only can sample a few times because it's expensive. After that, you run emulators again, and then you sample from the emulators. So it's a somewhat analogous method to the high tune process. Again, if you're trying to reduce the amount of time you're spending tuning the model, I won't go into the details, but the GFTL, like the GFTL experience, the IPSL experience is also that running these low resolution to medium resolution to high resolution models, the number of simulated years you have to run is quite a lot even for the tuning, is what this data is showing. In the interest of time, I'm going to skip this data on this study of using Lorenz 96, where we are, anyway, just briefly, we're using the history matching method to see how you would calibrate a couple system, because in a couple system, you have two components with different timescales. And if you're trying to calibrate them both, this is a paper that my postdoc Redwan Lagansat, who might be in the audience, and Julie Day and I are about to finalize and submit. So we're showing that in a couple model, you can actually also reduce the space, but there are some tricky issues involved with the fact that there are two different timescales involved that we'll explain in that paper. Again, I'm going to skip a couple of slides here. This is again, this is showing that in machine learning, you can, instead of simply finding a fit between the input and output vectors, you can actually try to discover equations that represent the equation well. I won't talk about this paper very much. This is an important result I want to show you, again, using deep learning. One of the criticisms of GCMs is that the column abstraction is not working anymore. But what you can do, which is an effective thing to do, is that you can say that in a deep learning problem, you can say that maybe my input vector for training can include my neighboring columns as well. So if you do that, they're using a convolution of 3 by 3, which means they're taking all their neighboring columns. You can still apply the same deep learning method, and you will get the result. And this paper by Wang et al. Is actually showing that this non-local parameterization is giving better results than a column parameterization. So this is pointing to, this machine learning is pointing to a way forward where we can still continue to work with the abstraction of a column, but you can generalize the way that the training is done. So, and you can also be non-local in time. The non-local in time, meaning that you include in your input vector values from the previous time step, or the 2 time steps ago even. So if you include that, then you can also have memory in the system. So the idea of the parameterization on the column can be retained, but the machine learning methods will allow you to generalize this to non-locality. So again, just some papers. I'll share the links so that you have access to these things. I want to switch gears and talk about the emulators from the other angle, which is the way IPCC is using them. So IPCC wants to get values and error bounds for every single forcing separately. So CO2, methane, N2O, each of these. So the way you would do this if you were using a GCM is that you would run a simulation where you're keeping all the forcing fixed excepting one, and you would see what error bars you get. What is the warming that results from this one single forcing agent? Obviously, if you have 15 different forcing agents, the number of simulations you have to do is quite astronomical. Most people cannot afford to do them. So but IPCC wants the data. So what they're doing is that they're using emulators, which are somewhat, to a certain extent, trained on output from models. And then they're using that to generate all these single forcing runs. Another thing that they did, which is that the spread in uncertainty in CMIP6, you're probably all aware, was quite high. There's some extremely high sensitivity models in CMIP6. What they said was, well, this uncertainty bound is too high to be useful. So what we will do is we will use the late 20th century to calibrate this complete distribution to get a constrained 90% range of models, which is considered most likely to be true. So now they're getting a narrower range of ECS, but this is again done with emulators. These emulators vary a lot. These RCM means reduced complexity models. There are various kinds of models, impulse response models and so forth, single column models even, but mostly what is used is impulse response models. They're obviously millions of times faster than a system model because they're simply a mapping from your forcing agents to your output global temperature. There is very little connection to climate physics. But as I quoted earlier, Ben Sanderson said in WGCM 24, the role of the ECM is increasingly as a target for robust emulation. I think that's very profound. Similarly, as we are arguing that cloud resolving models and LES larger dissimulation models can be used as targets for emulation, the ESM can be used as a target for emulation for building emulators. So that's kind of the argument. And we should, again, the paleoclimate, we have past warm climates. The models are not very good at doing these things, but it's very important. The data quality is not very good, so I would not recommend that paleoclimate be used for deep learning directly. But they do put constraints on sensitivity, and I think we should try to simulate at least past warm climates. They are showing, because you can consider them out of sample tests. That is, you train your model on present day, but you try to verify it using paleoclimate models. Right now, they don't do a great job. This is the PETM, the Paleocene thermal maximum that I showed. The data, which is just a few data points shown here, are showing that temperatures are pretty warm near the poles. We have, alligator fossils near the poles. So we know that the cold-blooded creatures could survive. So the temperatures are probably accurate. But the models are still showing that there is a large equator to pole temperature gradient, most of them. This is an old paper, but I believe the result is still valid. It's a 2011 paper. So my final remarks. My prediction is that in the ML era, there might be a divergence between climate models and weather models. The weather models are solving a stationary problem, which means boundary conditions are kept stationary. So I think we can use machine learning quite effectively. So there are articles arguing that this might be true all over the place. So there is an article saying, are we witnessing the dawn of post-theory science? That means we don't need theories anymore, we just need data. That's an extreme case. I think it won't work for climate for reasons I've outlined. I'll repeat again, computers are getting bigger, not faster. That means you can solve weak scaling problems in increased resolution, but you cannot do strong scaling problems. Some people argue that cloud resolving models do not have a tuning problem. I think that's completely not true. There is always a tuning. There is always a cost function. You're always minimizing or calibrating against some requirements, which is called fit for purpose. What we can try to do is to make the calibration process efficient so that you can do model development, as I argue, in weeks, not years. Any resolution, you will be doing model calibration. I'm repeating myself here. I am concerned that these emulators that are used by IPCC are decoupled from climate models. So I would like to recommend that we should try to make sure that we should make the emulators at least somewhat physically consistent with what climate models are saying. Otherwise, we have what I call epistemic risk. And I'll leave you with some references to read. The Chinese ladder paper, our GCMs obsolete, which is the preprint under review. We are working on the response to the reviewers right now. The book called The Climate Demon, Ben's talk, and then a workshop that's coming up at the end of August on hierarchies of models. Thank you. I'll stop here.
Thank you very much, Balaji, for this fascinating talk, at least in my view. Thanks a lot. So do we have questions or remarks for Balaji? Please just...
I am still screen sharing, so I cannot see anything in the chat.
All right, yeah, I'll try to read that loud. Let's see, give everyone the time to digest. Ben Sanderson, yeah, please.
Hi, thanks, Balaji. Can you hear me okay?
Yeah.
Yep.
Okay, great. Thanks, very interesting talk. So I guess my question is whether we're still, a lot of the novel progress which we've seen over the last few years has been about smarter ways to achieve calibration and to simplify the degrees of freedom in the calibration problem to get back to more plausible variants of the models we're already using. I guess my question is like whether we're aiming at the wrong complexity level for robust risk projection at all. So we have always been for the last 30 years at a point where we can only barely afford to run century scale or certainly millennium scale simulations. And one point which you made in your talk was that the more coupled the problem is, the harder the tuning problem is, and the more inter process dynamics you get between the ocean, the atmosphere, and the land, and everything. For CMIP class models, we're still not really operating in an emissions-driven framework, and a lot of our primary questions about global mitigation uncertainty rely on being in an emissions-driven framework. And so, yeah. So my main question is like, are we missing the main points here, in that we should be aiming to explore a class of low-resolution model, which at the moment we're ignoring across the board, across all centers, which really can't focus on this question of inter-process dynamics, mitigation, emissions-driven uncertainties, which explore hundreds or thousands of variants of process-based realizations of the system. We can obviously learn something from thinking about convection resolving models in terms of recognizing how processes work. But for me, the really deep uncertainties here are these highly coupled processes, and I don't see how emulation alone is going to get us there without introducing a new class of process-based model. Yes, that's my point.
Yeah, so I kind of agree. I do agree with what you're saying. So I believe that kilometer scale models and all that are useful for understanding certain kinds of physics. But I'll be very frank, I don't see the point running them at global scale very much, because you can run very short ones and you can learn a lot from idealized versions in small domains in highly idealized settings like RCE, radiative conductive equilibrium, for example. I do agree with you that these emissions-driven models, by the way, I don't agree that there's quite a lot of emissions-driven models. They're expensive, but a lot of ESMs right now are emissions-driven. They can be run both as concentration-driven and emissions-driven. They do exist. But we are not running enough cases of them because they're expensive. I totally agree with that. So I think we need, as you say, low-resolution, low-order models that include a lot of the processes we need, and we try to work on the emulation problem using those models. They're underemphasized. I think there is an overemphasis on high resolution and an underemphasis on low resolution, high complexity models. And how we kind of get the field to pay attention to these is a good question. I think we should the kind of articles like this, our GCMs obsolete, is trying to say, there's a class of problems you're ignoring, and they're actually very, very important for the climate problem. For the calibration, I would argue that it's very exciting, and I think there's solutions are possible, but there are still some unsolved problems. For example, when you have these models with multiple timescales, one thing we've known for years is that you can easily tune a model with compensating errors. You can create two errors and two different components that cancel each other and give you the right answer, so to speak.
Yeah.
So to figure out, so we're trying to find out ways using our calibration methods to detect compensating errors and try to fix them. We'd say that one of them is consistent with non-physics and the other one is not, for example. So I think physics driven with the concentration on physics. And then the other problem I'll say with the kind of emulators that IPCC is using is that the methodology is being used right now for GMST, for global mean surface temperature. You could do the same for any other variable of interest. What you will lose when you do that emulation process is that any sense of covariance between these output variables is lost because you're doing each of these independently. So I think the only way to get covariance is right, in my opinion. That's the only way I know is like enforce some kind of physical consistency on the model.
Agreed. Yep.
Yeah. So.
Thanks a lot, Balaji and Ben. Any other questions? Oh, Balaji? No. Yeah, I have to admit on my side, I had also similar questions on increased complexity on the one hand and this IMIC model that used to be very trendy at some point and are not at all anymore. And yeah, you in your talk, I think you emphasized a lot what we can gain or what we cannot gain also by increasing resolution, etc. But what about highlighting as well what has been done and big steps that have been made in the past thanks to IMIC models, for example, in terms of hysteresis and stuff like that? I thought this would have been interesting as well.
Yeah, so I mean, one reason I may have skipped through that very quickly. One reason I emphasize paleoclimate as something, again, I think we are not paying enough attention to across the field is because there's such an exclusive focus on making decadal predictions or something like that. So, I mean, my next slide, for example, I'm trying to say why the GCM, these broken columns, I think why they're important. You can take these kinds of models or those kinds of models, these CRM models, but you have to make them work for this problem. Sorry, that's a picture of Manabe. And then these kind of single forcing models. And I agree with you that, you know, these emulators are not even Emacs. I mean, there's the emulators that are used for IPCC are these models, FAIR and MAGIC. You can say they're kind of Emacs, but basically the complexity comes from the number of individual forcing agents that they're able to consider as inputs. That's where their strength is coming from. And again, I mean, I think connecting GCMs to these, and maybe EMIC is an intermediate step which sits right here where my mouse is pointing between these emulators and the GCMs. That whole thing, it has to be the hierarchy, and there some way to say that there is some physical way to get from there to here is important. And I think EMICs are a part of the story. I think you probably cannot make a direct jump from GCM to these emulators. You probably need a step in the middle on the ladder.
Yeah, thanks. Any other comments? No, not yet. Perhaps, Alessandra, I have to connect. Yeah, I have to connect to another Zoom. I guess implicit in all this is the fact that we could be using models for different means objectives through the CMIP. I guess implicit in all this is the fact that we could be using models for different means and objectives, although the CMIP project has taken over. Would you agree with this sentence from Alessandra, saying that in fact CMIP is kind of taking over all initiatives of various hierarchies and complexities of models?
I would agree with Ali. I think it has become dominant in the sense that model development has become geared at, we've explicitly started saying we're building a model for CMIP 7 and that sort of thing. And I think we should rethink that. We should be focusing on what are the scientific questions we are trying to answer. And maybe if you have 3 different scientific questions, they need 3 different kinds of models. Maybe one needs a CRM and another one needs a GCM and a third one needs an EMIC. but we kind of say we will build one model that will do everything for everybody. And CMIP has become so vast and that I think it is, I mean, again, I'm taking a lot of stands here. I think it has become over dominant, and it has stopped people from actually saying, what question are you trying to answer? Because you have a timetable for CMIP, and so that's what's driving everything. So I'm agreeing with Abby.
Yeah, thanks a lot, very inspiring. Any other questions from someone? Perhaps I can still go on, but please stop me. Yeah, you of course you know that. Well, you know that the French community, as any other community, is now trying to I mean, is having a lot of thoughts in how to respond to these digital twin initiative and all these ideas around having an ideal, very high resolution climate model that would allow to resolve all the questions at the same time. Perhaps the question is, how do you see the response to this initiative? I mean, here everyone listening to you are more or less climate modelers, I guess, or modelers. And how do you think we should answer that question? I mean, that questions and this initiative that is coming in front of us.
Yeah, so you probably are aware, some of you, that there's a kind of there's a few high-profile papers which have been written lately saying that we should put all our resources into this. And there was a WGCM meeting organized in March called the Future of Climate Modeling, where these people were quite vocal. I mean, I'm there. They're all people. They've been my colleagues for a long time. I know them quite well. Bjorn Stevens, Tim Palmer, Julia Slingo, etc. I believe it's a mistake if we just focused on high resolution, because I'm working on some projects where we're trying to use these models. And I can tell you that there's many problems which are not simply technical. I mean, of course, there are technical problems. It's a large volume of data and so forth. But people are trying to do machine learning. They're already having to coarse grain the data because it's too big, sort of thing. And then we are trying to get statistics from models that are running a few days, which is, extremely. We are not at all sure whether the sampling is good enough. I mean, really, I don't know what this is supposed to solve. What exactly this is high resolution is supposed to solve. I'm not clear on it. So it's important that there should be my belief is that it's important that we should, as a community, we should take somebody should take a public stance, and that I can include myself in that, saying that I don't think this is the answer to the uncertainties we are facing as a world community right now. That high resolution is not going to give you the answer, and it would be a mistake to take away resources from other ways of doing modeling in order to focus on this.
You do believe it's worth taking the time to argue, like to fight through semantical papers or position papers? Because another way of answering that would be to just continue doing our work and prove efficiency or prove robustness.
Yeah, it could be. It could be. The question is, do you see? I don't know the answer to that, but maybe somebody in the CLIMERI people, other people might have opinions. Do you see a risk that resources go away from other things? For example, people say, well, paleo is no longer interesting, so we don't give you any more funding for doing paleo research. So that's a possible risk, which I think would be bad for the field. Also the fact is that, if whoever attended the Future of Modeling workshop, even though there was people vocally making the case that we should put all our resources into having one center with one big model that will solve everybody's problems, there was a lot of pushback. I mean, there was a lot of opinion in the chat and in the discussion saying that I don't think this is the answer. So if there is such a widespread feeling. How come it's not public? How come we're only hearing from the people who are saying we'd only do kilometer scale and nothing else? Is it, I mean, I don't know the good answer to that, Juliette. Should we just go about our business and do our work, what we find scientifically interesting and important, and just let it go? Or should we take a public stand? My way of taking a public stance is writing this paper.
Yeah.
Mhm.
Thanks.
Yeah.
Thanks a lot. Any other thoughts or questions or comments on the future of our GCMs? Compliments? No?
Okay, thank you then.
Okay, thanks a lot, Balaji, for this inspiring talk. And yeah, see you soon, hopefully, if you come back.
Yeah, by the way, my MOBGA is not yet finished, Juliette, so I still have another year and a half, so I'm hoping to be back in March.
Okay.
March of 2023, yeah.
Thanks.
Yeah.
All right. Thanks a lot, and good afternoon to everyone. Bye-bye.